Okay, so if not, so yesterday we were discussing. So I'll in the end, towards the end, we were discussing about the difference between a direct and indirect band gap semiconductor. So when we talk about this band gap, so instead of representing it in the schematic uh, band structure that we have shown so far, so what normally we plot is electron energy as a function of momentum, and the momentum for an electron in an energy band, we can write it like H cross K, where your H cross is, or H cross or H bar, so it is nothing but H by 2 pi. So this is a representation of that. And K is your wave vector of the electron, because electron we are considering it as a quantum mechanical particle, or it's like a behaves like a wave with a wavelength lambda, which is the de Broglie wavelength of the electron. So we can write the momentum. So you know that you normally write your de Broglie wavelength as h by p. So if you rearrange, so you can get this expression for momentum p. So many times this since p is represented like this for a wave, so rather than plotting e as a function of momentum, so we plot e as a function of h cross k, or simply e as a function of k, because h cross or h bar is a constant. And from the energy dependence, we know the relationship between energy and momentum is like this, and this is simply h cross square k square by 2f. So if you plot energy as a function of k or h cross k, so it is always will be, it's a parabolic in nature. This is not always true, but this is the best approximation one can have when we talk about electrons in metals, or in mostly like conduction, or we consider about the free electrons when we are talking about electron which are almost like free electron. Okay, so the same thing we can do for the holes as well. So in case of hole, so this picture will be inverted, so the relation will remain the same, because the energy and everything, so it behaves exactly like electron, uh, but with the opposite charge, and the momentum is opposite, and therefore this is the hole in the valence band normally is represented by inverted this parabolic function. So this is for the, so this is, we call the valence band, and this is the conduction band, and this is your, the difference of the bottom of the conduction band to the top of the valence band. This difference is your band gap Eg. Okay, so which is Eb minus Eb. This is your band gap. Now, when a transition happens from the conduction band to the valence band, so this is a, let's say, recombination process is taking place. So if you have an electron and it jumps to the valence band and occupies a empty state, which is basically your hole, so that means it is recombining with the hole. So in the process, it will release a energy, a photon, which is with an energy h of f, which is equal to E. So this is a standard picture which happens in materials which are known as direct band gap semiconductor. So these are also, so this process of recombination is known as a direct recombination. But so example are, so if you take a gallium arsenide, okay, or aluminium arsenide, okay, so these are some of the semiconductors which are actually show a direct band gap. But if you take silicon, this picture is different. So in case of silicon, what happens? So if this is your, let's say, the bottom of the conduction band and the top of the valence band, so they are at different k values or momentum values. So that means this bottom of the valence band or conduction band and the top of the valence band has a different. So this is at kCb, this is at kPb. So they are different. And of course, the band gap is it's still the difference between the bottom of the conduction band and the top of the valence band. That is still the band gap. But now, when a electron goes back to valence band, there is so energy, of course, will be the same, but the momentum will be different. Okay, so there is a change in momentum, because if this electron goes to, so let's say it jumps to the state here. Okay, so now the momentum of the electron is actually has changed in the valence band, because the electron needs to go here, because the hole that is available, because all these states would be probably filled by electrons. So electron can only go to this, recombine with the hole here, which is the empty state, and therefore it has to change its momentum in order to do that. So in this process, your momentum is actually not, the change in momentum is not equal to zero. It is not conserved. And so these kind of materials are known as indirect band gap materials. And this is a process, in this recombination process, it is an indirect recombination. Okay. And in the earlier case, what you have here in a direct band gap, you have a emission of photon. Okay, so this leads to a emission of photon, and the photon or the light that is generated has a energy equal to wavelength. But most likely in the case of indirect band gap, so you may not have a generation of photons, but what you have is you will get a so energy which will be released to this. So let's say we write this ECB minus EVB will be released in some form of some energy H omega, let's say, and this will go to the lattice or your atomic vibration. So it is more like a thermal. It is more like a thermal energy that is being released, or a heat that is being released in this way. So it is not a release of a photon, but it is a release of a heat or thermal energy. So this is the difference between your indirect and direct band gap material. So here the example, you have silicon and germanium. So therefore, if you want to use a semiconductor for a light emitting diode, so where you want to have a LED you want to make out of this semiconductor devices, so in that case you would prefer to use a direct band gap semiconductor such as gallium arsenide, and that is actually what in LEDs that is actually used. So let's look at the, so we have seen certain example of this semiconductor material. So let's look at the broad classification of that. So the semiconductor, basically the family, you can have a simple or a elemental semiconductor. So it's known as an elemental semiconductor, or just a simple semiconductor like silicon and germanium. And the other type is known as a compound semiconductor. So again, compound because you have more than two elements in the material, and the combination, normally two or more than two. You can have also more than two elements, which is known as a compound semiconductor. So examples are gallium arsenide, indium phosphide, zinc sulfide, zinc selenide. Okay, so even in the same, so you can have silicon carbide, silicon germanium. You can also make a compound semiconductor out of that. So how do we get this combination and we say this is a becomes a semiconductor? So here you see this 3 and 5 something, so which is actually, or here you see 2 and 6. Okay, so this is related to the periodic table. So if you go to the periodic table and this group 3, group 4 and group 5 elements, so which I have just taken only those parts, so not the whole periodic table, but only the elements which belong to this group 3, 4 and 5 in the periodic table. So what you see is group 4, this is your typically elemental semiconductor or the normal semiconductor. Okay, so silicon germanium, which is the most famous one. Then you can actually make a compound semiconductor between group 3 when you put a group 3 and group 5 elements. So then you can get a compound semiconductor. Or so the example, as we saw, it's a gallium. So let's say we take gallium and arsenic, so you get gallium arsenide. So similarly, you can take gallium with nitride, nitrogen, so you get gallium nitride. So that is also possible. So gallium phosphide, that is also possible. So these combinations can lead to new type of semiconductor material. So similarly, this aluminium can also be mixed with this. So all semiconductor may not be useful. Okay, so you can make them, but all semiconductor may not be useful, or sometimes also not that easy to make or synthesize. Okay, so that is also another challenge. Now, similarly, you can also mix this group 2 and group 4, group 2 and group 6. Sorry, so group 2 and group 6. So this is this typical zinc selenide. So sulfide is missing here in this 6th column. So this is, again, you can get zinc sulfide. So cadmium, for example, these are cadmium selenide, cadmium sulfide. So these are very really famous semiconductors which are used mostly in for optical devices. Okay, so in terms of like in quantum dots, for example, you get this semiconductor cadmium selenide or cadmium sulfide. And also one thing which is interesting, that when you take a group 4 element like silicon or germanium, now you want to dope. So you want to make it p type or n type. So basically you choose something from B, group 3 element like boron, or group 5 like phosphorus and arsenic. So similarly, if you have a gallium arsenide, okay, and now you want to make a n type or p type, so you can actually use silicon as a dopant. Okay, so in that case, if you put silicon, because it's again, so you can have extra electron or extra hole in the material, and then you can make it p type or n type. So this is a very interesting thing which you can play with this material, and you can make doping in these materials as well. But most of these semiconductors which we are talking about, this 3,5 or 2,6, so they're known as 3,5 because they belong to the group 3 and group 5, or group 2 or 2 6 semiconductors, these compound ones, are not really used in devices like transistors, okay, or for this IC that we use. So they are mostly used in like lasers, or mostly like if you want to get some optical or like solar cells. Okay, so these kind of applications, these materials are normally used, or some photo detectors as well. Okay. So here again, this is a table with the compound semiconductor. So we saw that we can combine two elements, so and we get this different kinds of binary compound semiconductors. You can also combine more than three elements, so which we call the ternary semiconductor. So here gallium arsenide and phosphide, gallium arsenic and phosphorus, that you can combine. So similarly, aluminium gallium arsenide. So this you can also combine and get a semiconductor. So you can take even more than, so about 4 elements. So this is also another possibility. You can, so by mixing more elements, you can get this new kind of semiconductor material. And what is so advantage with this binary, ternary, or quaternary systems, that you actually people are exploring these new or different kind of semiconductors to actually obtain or change the band gap. So when you take a certain mix, certain material, so you get your band gap is defined. Okay, so that defines your semiconductor. So now if you want to change or vary this band gap, so you need to mix new elements and make new semiconductors, and that is how you can vary the band gap. So here, the reason why we are exploring these many different kinds of compounds is to vary the band gap. Okay. So this way you can actually, so when the emission takes place or recombination happens, the photon that is released will have different wavelength. So by varying the band gap, so you can vary the color of light emitted. So you can get a blue color or red color or green color. Okay, so if it is in the optical region, you can even get infrared, you can get ultraviolet. So different frequencies or different energy photon you can get by varying the band gap. So, so in semiconductor, so one in research, so one very fascinating field is how you can control or vary the band gap using as small number of elements as possible. Okay. So I think in so you can vary the band gap also in many different ways as well. So this is one way where you can combine different elements in different and get a new compound semiconductor and vary the band gap. So when we look at the properties of some of the semiconductor materials, so here this is a table where we it is shown the most commonly used semiconductor materials. So germanium, silicon, and two compound semiconductor, indium phosphide and gallium arsenide. So when you look at the band gap here, so let's look at the band gap. So you see there is a variation in band gap. So germanium has the smallest band gap, 0.66. Silicon has about 1.1 electron volt, and so on. So the electron, the work function is different. The number of this effective density of states in the conduction band and in the valence band, so they are different. So everything was different and depends on the material that you are you have chosen. So the concentration, imprinting concentration is different. So you can do all these calculations. So some of the examples that I have told you to solve, so that when you do that, so you will understand or find out how you can calculate these values. So the most important parameter is the mobility. Mobility is also varies hugely. So for germanium, This is the electron mobility is very high, 3,900 centimeter square, volt inverse, second inverse, compared to your silicon. Okay. Uh, and in case of gallium arsenide, you have the highest mobility of electron. So if you want to really make a very fast device where you really need transport should be as quick as possible, so the device operates really fast. So in that case, you would prefer gallium arsenide based device because it has the highest electron mobility. So similarly, the effective mass are also different, and so on. Now we have so many different kind of materials, but so far in electronic industry, silicon is the most preferred material that is used extensively. Okay, so this is like the one of the single most used semiconductor material in an industry. So why? What is the reason? So, so there are few check boxes which needs all those check boxes. If they tick, so then we would say that yes, silicon is like the material is a preferred material. So what are those check boxes? So let's look at the first is the band gap. So silicon has a moderate. So what we are comparing is only about silicon. Okay, silicon has a moderate band gap. So it is not too high or not too low. Now how it helps? Now if you have a very small band gap, so for germanium it is 0.66 electron volt, and for silicon it is 1.1 electron volt. Now if you take germanium and since it is a band gap is smaller, so what it means, let's say you have a device, like any P type or N type, and then what you have is at a temperature T, so germanium will have more electron hole pairs, okay, compared to silicon, correct? Because the band gap is small, so the thermal excitation will lead to more number of electron hole pair in germanium. And what it means, so when you are looking at the device, so you would require that, so both are basically your charge carriers. Now if you have a, let's say if you take an N type germanium and silicon, so in this case, so you have more, the number of holes are more in germanium. So let's say number of holes is more in germanium compared to number of holes in silicon, because now you have more number of electron hole pairs, so electron number will be high, but you will have more number of holes as well also in germanium, so which is not desirable in N type semiconductor. Okay, so what it means, so it will lead to a leakage current. So this minority charge carrier, this holes which are present in the N type semiconductor, so they will definitely move when you are applying an electric field. So it will lead to a leakage current, and therefore germanium leakage current, the leakage current in germanium is high compared to your leakage current in silicon, which is not good for your device. So you want only the electron should move, so not the hole should move if it is a N type. So if the hole moves, also contributes to the conductivity, it basically will reduce the current in the device. So this is the leakage current. This is the contribution comes from the leakage current, and that's why earlier, when in the beginning, so people were exploring both germanium and silicon. So only because of this reason, germanium was discarded and silicon was preferred in 1960s and 1970s. Because at that time, so the compound semiconductors were not that well understood. So, and that is how silicon became like one of the primary uh, material for semiconductor industry. So germanium lost, although it has higher mobility. Okay, so the electron mobility is high, but due to this high leakage current, it was not preferred. So the second checkbox we say is, so let's go to the next page. So the second one, like if we say, talk about the mobility, again, for a fast device, you need a higher mobility. So silicon is not the best in that way, but it is still acceptable when we look at most of the operating speed of devices. So silicon, the mobility is still acceptable. Okay, so you can say it has an adequate mobility. So silicon has an adequate mobility for most of the devices or operating time of devices that we are using. But if you need really a fast switching device, so probably you will go for gallium arsenide in that case. Another point in favor of silicon is ease of processing. Because when you are making these devices, you have to go through many mechanical, chemical, thermal processes. So the processes can be a mechanical, chemical, or thermal process. So one example, let's say, let's talk about doping. Okay, so ease of processing, or let's say we say if you want to dope a semiconductor. So doping is really can be done in a very controlled and robust way in silicon. So normally you do doping by a diffusion or ion implantation. Okay, so ion implantation means like you take this arsenic ions or your boron, so you get a charged ions and then implant. So they have certain energy and they can go and penetrate into the silicon and get deposited in silicon. Okay, so this is how you can get doping. So when you are doing this processes, normally you will do at a higher temperature. Okay, so and if the material doesn't is not stable at high temperature, so the typical temperature would be like you can go up to like 1,000 degree Celsius, let's say not 1,000, but let's say about 1,000 degree Celsius. This temperature or the thermal range the material normally will see during a process, during a device fabrication process. And silicon is really good in that sense. So silicon has a good thermal stability. So that means the silicon doesn't really melt or break so easily thermally, and that's why it is you can do all this processing and it will be still, it will retain the properties of silicon. Okay, so that's why it is a preferred one. So silicon has a good thermal stability, means the silicon atoms, so they don't move or diffuse that fast. Okay, so the diffusion is slow. Which is you want. Okay, and also it doesn't, let's say, evaporate easily. Evaporation is low. But if you compare, for example, gallium arsenide, okay, so if you take gallium arsenide, which has a better conductivity or uh, better mobility, but if you do a high thermal treatment, so if you increase the temperature, so what happens, your this arsenic atoms are not thermally stable, okay. So most of this is like one problem with many of the compound semiconductors actually. So you cannot do a high temperature processing of these materials. And also arsenic will evaporate fast. So you will actually, during the heat treatment, so it may happen, the arsenic will evaporate and then you have a semiconductor with a lot of defects. Okay, so that's why silicon in that way is robust and thermally stable. So that is like one biggest advantage of using silicon in most of the electronic devices. Another thing which we haven't talked about, but I'll just mention it. So something known as a minority carrier lifetime. So this minority carrier are always like, if I take N type, so the minority carrier are holes. If I take P type, minority carrier are electrons. And normally in silicon, this minority carrier lifetime is large. So what you need is, the silicon has a larger minority carrier lifetime. So this way, so that means larger lifetime means, so if there is a defect or some impurity is there and your electron is trapped there or your hole is trapped there, so it will stay there longer. So that means the recombination process is, the probability of recombination is small. So this means the recombination probability is low. So which is you require for most of the device application, unless you are saying you want a light emitting diode or something. So most of the like transistors that you are using, so what you would require is that the recombination probability is low, so that the charge carriers, they are actually participating in transport or moving from N to P to N or something like that, instead of they are recombining with the holes. Okay, so this is why a large or a longer minority carrier lifetime is preferred, and silicon actually is good in that sense. Okay, so another factor is, already we mentioned that for semiconductors. So in the processing part, so when we talk about, so we haven't discussed about this MOSFET devices. So many times you use a insulator which is a part of the device. It is like a part of the semiconductor, your transistor. Okay, the MOSFET, which is known as your metal oxide semiconductor, and FET stands for field effect transistor. So you will see what this MOSFET means after this. So MOSFET, normally we use a silicon oxide as an insulator. So silicon oxide is used as an insulator, which is really like one of the easiest way to grow silicon dioxide compared to any other insulator on these devices. Okay, so since we have a silicon, and then it is easy to grow a silicon oxide insulator compared to any other oxide material, and it has also very good properties in terms of like the permittivity is high. It is also it can withstand a large electric field, so that means it will not. So this is known as a high breakdown voltage. That means if you take a thinner silicon oxide, so you can apply a very high voltage. That means, and it will not, there will be no dielectric breakdown of the material. Then another point about silicon is it has a good thermal conductivity actually. So silicon, in fact, has the highest thermal conductivity amongst all semiconductors. And this means that when the device is in operation and you generate, because during the operation, so you will generate a lot of heat because of the resistance, and this heat need to be taken away from the device where this operation is or this transport is happening. That, and silicon, since has a good thermal conductivity, so the heat generated in the process will immediately be carried away, or we can take it away from the device, and then the devices, they run faster and longer. So the lifetime of the device will be, we can increase the lifetime of the device, which is not true for any other material. Okay, so this is another big advantage. And another advantage of silicon is silicon is mechanically stable. So it has a thermal stability as well as it has a very good mechanical stability as well. So that means when you are doing some device fabrication, some processes, so you can actually make, or we can have large silicon single crystals we can grow, which is of the order of, let's say, 200 to 300 millimeter in diameter. Okay, so you make these wafers which are 200 to 300 millimeter in diameter. But in other cases, it is not that. For example, in germanium, or if you take gallium arsenide, so you cannot make these big, huge single crystals. They will really break easily. Silicon is still brittle. I mean, it is not like diamond, but better than all other semiconductors. Okay, so we are comparing this with other semiconductors. So compared to other semiconductors, it has highest thermal conductivity, so better stability, thermal and mechanical stability. And that's why it is one of the preferred material in industry so far. So there are many candidates with better mobility, higher mobility, and band gap is better and so on. But the technology, the industry level technology that is required for large scale production is no one can beat silicon in that. So that's why silicon is still ruling. The last, like it started in 1960s and still used like that. Okay, so next we will talk about the field effect transistor. So we'll give a brief introduction to that and continue with this in the next class. So So this is so you already know that after you dope your semiconductor, you make P type or N type. So then you basically you want to put them together so that you can make a diode, you can make a transistor, okay, like a bipolar junction transistor. You have already read about that. And then you have certain characteristic, like you apply a voltage across the junction and you get a current. Okay, so all those characteristic will which you can use for as a as a rectifier or amplifier, or you can use it for uh, like switching, like a switch. Okay, so all this you can do using your when you put your uh, p-type and n-type semiconductor together and make junctions. So in that direction, this field effect transistor is something similar. So basically you can make, so there are two kinds of broad category of this field effect transistor. So one is known as a junction field effect transistor. So this field effect transistor, the short form is FET. So you have a JFET, and another is known as, another design is known as a MISFET. And what is, so here I stands for insulator, and a metal insulator semiconductor field effect transistor. And in this MISFET, if the insulator is an oxide, insulator is an oxide, so like silicon dioxide, so that is known as a MOSFET. Okay, metal oxide semiconductor field effect transistor. So we will look at this one about this device, and briefly will because the focus, we will put more focus on the material aspects. But before that, just I want to give a brief idea how this device looks like. So when you take, this is a schematic diagram of this MOSFET. So what you have is uh, so you have a p-type substrate here in the bottom. So this p-type substrate, and then you have a n-type or heavily doped uh, n-type material, and another which is known as the source here. So on the left side, this is known as source. And then on the right side, again, the same heavily doped N-type material. So you call it a drain. So now you can change it. So the what we are showing is only this one kind of device, which is we call a NMOS. Okay, so you can also have a PMOS as well, where you have uh, N-type substrate. So here we are using a P-type substrate. Okay, so instead of that, you can use a N-type substrate, and in that case, source and drain will be heavily doped P-type. Okay, so that will be a PMOS. So we will take this example of NMOS and understand the device, and it will be actually true for the other one as well. So you have a P-type substrate, then you dope heavily with N-type, so you get source and drain. And on top of this device, so you have this insulator, so which is your oxide, silicon dioxide. Okay, so this is your oxide layer on top of that, and then you put a metal contact, which is your gate. So this is your gate, so which actually is joining your semiconductor is on top of the semiconductor. So the source is connected to the N-type, drain connected to the N-type within the P-type material, and you have a gate. And this is how it is represented here, this MOSFET in an electrical circuit. So the operation is very interesting here. So how you can get a flow of current, basically the flow will happen from the source to the drain. So there is a current that will flow from source to drain when you are applying certain voltage across all these across the gate and source and drain. So you will see how that happens. So what is the circuit connection we will see. But one thing is pretty clear. You can see already that since you have a p-type and n-type, so you have a junction and immediately you have this formation of depletion layer. So this gray area that we have here, this region is your depletion region. Okay, so this is automatically will form because of this junction. Yeah, this we already discussed about the design of the MOSFET. So this is again a schematic diagram of that. So you have a source, you have a drain, source, drain, and then you have a dielectric, the silica or silicon dioxide here. And the material what is used for a gate, this is a polysilicon. So this polysilicon we discussed, it is a heavily doped silicon, which is a degenerate semiconductor. In fact, it is almost behaves like a metal. So it is a heavily doped semiconductor. This polysilicon, and it is known as polysilicon because it is so it is a polycrystalline silicon actually. So here the silicon is a, this is a single crystal. Everywhere it is single crystal, so only this polysilicon is polycrystalline. So in this conventional MOSFET device, so what you already see, like if I take silicon and I can make a device using silicon only. So some form of silicon I can use and get this device. So I have a substrate which is silicon. Then the p-type material is also silicon, n-type also silicon with some doping. The oxide that I'm using is also silicon, some form of silicon. This is silicon dioxide. And the contact that I am making is also a kind of silicon. It's a polysilicon. So that's why this silicon is has been preferred for this MOSFET. Okay, so because of you can use some form of silicon, so you can then, let's say you have a silicon on the surface and you oxidize and you get a silicon dioxide. Okay, but if you take another semiconductor, so this is not going to happen. So you probably have to put maybe another material as a as an insulator, and then it is there can be issues with how you can grow that oxide layer on top of that or dielectric layer on top of that. So another replacement which people have tried, which is not conventional, so where you use a this oxide, not an oxide, but you use a material with a high permittivity or high K. So this is, they are known as high K dielectric. So the dielectric constant is high. So use those kind of materials. So instead of silicon dioxide, okay. And then in place of polysilicon, you use a normal metal electrode like a copper or aluminum you will use in that case. But there you are using, in the other case, so you are using other materials, but if you are using only a pure silicon based MOSFET, so everything is based on some form of silicon. So that's why it is really good for large scale fabrication. Okay. Okay, so this is, but how this MOSFET device operates? So how do we get a current from source to drain? Because when we have made the device, we see it is like a so N and P type, and we have basically, so you can say this is like N plus P N plus. We have here a transistor. So how we, and what is the role of the gate? What is the role of this oxide here? So why we are putting a oxide here? So I think we will talk about that in the next class. It's already time. We'll start with that in the next class. And in the next class, I will also, so next one is the last class. So I will discuss about the MOSFET device and the materials that are used in MOSFET. And then I will give a brief introduction to two-dimensional materials. Okay, so how two-dimensional materials, like the novel materials that are now in the research phase, how they are being used for different devices. Okay, any question? Okay, so if not, so thank you. We'll meet again then on Monday.